We are now live. So I'll give a few minutes. Hello, everyone. Welcome to today's Lunch and Learn session. We're giving everyone a chance to join and settle in, so we'll wait a few minutes. But today we have an international speaker. So the question for today is, where are you guys joining from? Would love to know that. I'm going to put that in the chat, and you can answer. You can answer that as well. So, hi, Ty. Shout out to Google. And we'll wait probably another maybe 3 or so minutes, and then we can jump right in. Seattle. We see Seattle being represented. LA. So West Coast. No one from the East Coast or maybe international. Um, Boston. So finally, we have an East Coast representation of Boston. So welcome, William from Boston. And we'll give everyone maybe another minute or so, and then we can jumpstart the exciting lunch and learn today. All right, we're going to go ahead and get started. Once again, welcome to today's lunch and learn. The title, From RAG to GraphRAG, a smarter AI retrieval. Before we get started, I wanted to do a few housekeeping material, a few housekeeping details. So this is an interactive session. Please feel free to post your questions in the chat window. I will be corralling your questions. Oh, and I forgot to introduce myself. My name is Denise Moxie, and I am the Director of Product Marketing at Aperture Data, and I will be your host for today's event. Um, Before we jump into it, wanted to just give you a few housekeeping rules, details. Post your questions in the chat. Post at any time. It's an interactive session. So I'll jump in the flow of conversation to have your questions answered. As promised, all recordings of the Lunch and Learn will be available on demand and after the session, and that also includes links to the resources for the collab notebooks, the slide decks, and any other information that you might need. For today's Lunch and Learn, the Luma link actually has the notebooks that Ayesha will be reviewing. And I'll also post the GitHub repo link in the comments so you can follow along. Throughout the Lunch and Learn. So, once again, thank you so much for joining us. Today's exciting Lunch and Learn in a partnership with Google is around from RAG to GraphRAG, a smarter AI retrieval. In this Lunch and Learn, we have two dynamic speakers um, that will explore how to build a knowledge graph with Google Gemini and ApertureDB. And then we'll take the knowledge graph to the next level by building a GraphRAG application and then comparing quantitatively and qualitatively um, the metrics between a plain vanilla RAG and a GraphRAG. Um, Next, we will sort of have a recap and some highlights about ApertureDB. And then finally, a Q&A and a wrap up. I am pretty excited today because we have two guest speakers. Our first guest speaker is Ayesha Imran from Pakistan. So awesome. We have an international speaker. Ayesha is a recent grad from NED University in Pakistan. She's also a community member of Aperture Data. Her degree software is in software engineering, and she has extensive experience in full stack development, LLMs, as well as Gen AI agentic solutions. She is the co-founder of Byte, an AI nutrition app. She's also the winner of a Cohere hackathon and a finalist in the Google Solutions Challenge. On the other side, we have Gautam Saluja, a senior software engineer from Aperture Data. He's one of the chefs behind some of the cool technologies that we're cooking up just for you. Most recently, he has worked on a series of ready to use out of the box workflows that simplify data management tasks for your AI and agentic solutions. So, with that, we're going to get started and I'll pass it on to Aisha.
Hi everyone, I'm Ayesha. I'm super excited to showcase this implementation of a knowledge graph automation with GraphRAG that I created a few months ago with ApertureDB. And let's jump in. Okay, so as the title suggests, today we're going to explore basically two things that are sort of intertwined. So first is automating the creation of a knowledge graph, and then using knowledge graph in a RAG pipeline to essentially apply GraphRAG. And then we will also compare it with vanilla RAG. Okay, so to start off with, let's actually do a little bit intro into what knowledge graphs are in the first place. So basically, knowledge graphs are basically these interconnected network. It's an internet connected network of entities, which are basically the nodes, and these connections are called the edges, which connect the entities together. And these connections are sort of like relationships between entities or nodes. So the reason why these are so useful and have various use cases is because we can represent different nuanced relationships and like rich relationships between entities, which like otherwise maybe in just simple text and all, it's not very easy to convey these relationships. And also like these nodes, we can see these nodes and connections, but these nodes can also have their own properties, which again makes the entire knowledge graph even richer. And that's also like how our knowledge graph is like, because each entity has its own set of properties. And there has been some like implementation of RAG like using graphs, and there is evidence according to like different research works as well that this actually does help a lot in enterprise um, use cases, especially when we are dealing with financial or legal medical sort of data. So I'm pretty sure that pretty much everyone must have some knowledge about retrieval augmented generation. It's been really trending, and it's really been out there since the last couple of years. So essentially, retrieval augmented generation is simply like providing some sort of knowledge base to an LLM to generate answers using. So instead of relying on its own data, the LLM can fetch relevant knowledge based on user query from its knowledge base, and then it can generate a grounded answer with citations, and that obviously reduces hallucination as well. So GraphRAG is just an enhancement of plain RAG, and the way it works is that it enhances RAG in a way that instead of performing RAG over flat documents, we can perform RAG over knowledge graphs. So when we can retrieve top k nodes which are semantically similar to the user query, and then we can basically find which further entities are connected to our top k retrieved entities, and we can pull them in as well in the context. And this basically captures some very rich sort of, or nuanced sort of relationships that vanilla RAG does not. um, this is and the most optimal use case of GraphRAG is in combination with plain RAG. So you can say it's sort of hybrid RAG, where you first do top k retrieval like you do in vanilla RAG, but then you hop to the entities connected, whatever the entities are connected to, and then you fetch that in as well. So ApertureDB is perfect for this use case because it is a unified store that has multi-model and AI native capabilities. So you can store all sorts of data in one system, and you can connect it all together. And your retrieval can be super customized, and you can even make a graph using all this multi-model data. And then ApertureDB is also embeddings native, so it's not like you have to store your embeddings in some other vector database. ApertureDB provides uh, uh, embedding support through descriptors, which are embeddings, and descriptor sets, which are basically vectors, a vector store sort of index. And it also provides built-in vector search capability, so you can perform vector search through ApertureDB. And yeah, you can combine your knowledge graph with vector embeddings, which of course is necessary if you want to perform a GraphRAG over the curated knowledge graph. And ApertureDB really streamlines it by giving the ability to make connections between entities in the database, and these connections can then be traversed. Again, this is something very important and necessary when we want to do graph traversal for GraphRAG. So two other things that we need for our workflow are basically we need an LLM, and we need this LLM to extract all of the entities and their properties and the relationships between entities in our data. So we need a very powerful LLM for this, optimally with a large context window, because if you want to process a large amount of data, then we need a large context window as well as some powerful extraction capabilities. And the other thing that we need is an embedding model to convert our textual data or other sort of data into vector embeddings for semantic search. So for this workflow, I used Gemini 2.5 because it has a very large context window, which is perfect for handling a large amount of data, and it has it has very powerful capabilities because it can extract entities and relationships and their properties in a very robust manner. And for embeddings as well, I'm using Gemini embedding models, which is actually quite recent, but it's also very powerful and it's configurable. So you can even change embedding dimensions to based on whatever your requirements are. Now, before we dive into the actual notebooks, I would like to give you a very high-level overview of the entire workflow so that we can have an understanding of what we're going to be looking at, and then we'll further dive deeper. So first of all, it all starts with your raw documents. Currently, we're processing raw PDFs. And in fact, the PDF that that I'm going to walk through with is a 42-page long PDF, so it's quite large. So we start with a raw PDF. Then, first of all, we pass in this data to basically in different parts. We pass it through an LLM, which extracts entities and relationships between them, as well as properties of the entities. Once all of this has been extracted, we connect the entities together using whatever relationships have been defined between them, and this essentially creates a knowledge graph. Now comes in ApertureDB. So what we do is that we store this knowledge graph in ApertureDB as well. Optionally, we can store the raw documents themselves, and we can make connection between the knowledge graph and the document. So if, let's say, you want to see the entire document for some reason, you can easily do that. Next, of course, to enable, now this knowledge graph is already quite useful in itself, but for performing GraphRAG, we need to have vector embeddings. So what we do is that we convert these entities and their properties into basically vector embeddings, and we index them, and then we also store those embeddings into ApertureDB, and of course we connect with them with the original knowledge graph as well. Then for the retrieval augmented generation part, we have the user query. So the user sends the query to the large language model, but before the large language model generates an answer, the query is also sent to the vector data to ApertureDB, and vector search is performed to fetch the context needed to answer the query. And for this, again, this is where GraphRAG comes into play, because we fetch the top key entities and then we traverse the graph to find the connections as well, and then we feed that into the large language model along with the user query, and the large language model then generates its answer. So this is the high level overview of the workflow, and over here I would just like to point out that just to like showcase the importance and the strength of GraphRAG, there's this video I found it really interesting. It's by NVIDIA, and they also have implemented a very similar workflow, and I actually came across this after I had already done this entire project. And I found it really interesting because they also use a very similar, pretty much exactly the same workflow as I am using. They also use LLMs to extract entities and relationships between them in the same manner, and then they create a knowledge graph and they perform GraphRAG over it. So I would really recommend going through this as well. At the end, they also mention a lot of tips to scale knowledge graphs to production ready systems and enterprises. So yeah, this is something that really showcases the potential of GraphRAG, specifically hybrid RAG, because they also combine vanilla RAG with GraphRAG. So how important and useful it can be for enterprises.
So Haisha, before you continue, we have one question, and that is it a human that is creating the graph schema or reviewing it? And that comes from Amy. Thank you for that question, Amy.
Right. So this is yeah, a good question. So um, this is completely automated. Right. The what my implementation is, it's like completely automated. Will when we further go into the workflow, you can see how the process looks like. But basically, the LLM itself extracts everything. However, this is because I implemented in a way that any data can be used for creating the graph, right? And anyone can use whatever data they want. However, if we have to use this in like a production system or for enterprises and stuff, then in that case, it's definitely because these enterprises will already have some idea of what their data looks like, and they will be able to define some sort of classes and properties and stuff to constrain what the knowledge graph should be like. So in that case, some constraints, human oversight can be included. Yeah. So, but currently we're delegating it to an LLM. However, I'll further expand upon this as we go on.
Thank
Uh,
you.
okay. So with that being said, let's start with part one and like part two. They're in the same notebook. So and this is I'll go over this diagram. So in part one, we will extract the classes. Like basically the categories of entities, and then the entities and their properties themselves, we'll extract these. And in part two, we'll create relationships between these entities, and basically this will itself curate the knowledge graph, and then we will ingest everything into a ApertureDB database. Right. So yeah, so to look at the diagram, we zoom in a bit. Okay, so like I said, we'll start with the raw document. Then in the first pass, we will that we provided to Gemini, we will have it extract high level classes. So these classes are basically sort of categories. So it will go over the entire document in one go, and it will identify what are the possible classes that all of the entities can be classified into based on this document. And these and whatever classes have been extracted, all of the entities that will be further instances that will be further extracted, they will fall into one of these classes. So this is a point where right now this is something that an LLM is doing. However, if you already have a good a good understanding of what your data is like, let's say a financial firm or a legal firm, and they have some they have some familiarity with their data, they can in this step they can define the classes themselves to ensure that whatever entities are extracted, they are part of one of these classes that have been defined by them, and this gives a lot more control over the knowledge graph. Right, so once we have the classes, and at the same time, not just classes, but the LLM also extracts what possible properties can be associated with that with entities of that class. Now entities of a class may have either no, none, one, or some of these properties, so there's no restriction, but this is basically a comprehensive set of properties that can possibly be defined by entities of a particular class. Once we have these classes and possible properties defined, we chunk a document into a fixed so we fix a size, and then we chunk our documents into this fixed size, and in parallel we again send these chunks as well as the list of classes to Gemini, which now in this pass it basically extracts entities of all of the classes, and now as well as their properties whichever are present in the chunks. So now what we have is that we have all of our entities, or you can say the nodes of the knowledge graph, and their properties which are all defined now. That's what we have at this point. But now since parallel processing was done, we have to consolidate and we have to make sure that there are no duplicate entities, because obviously in your document you might have the same entity mentioned multiple times and it might be in multiple chunks, so you can have multiple instances of the same entity. So we consolidate, and we take union of all of the properties to make sure that no property is lost, and then we assign unique IDs to our entities for later identification and for defining relationships and all. Now in the second, and this is part does not need any LLM, we can manually do that. And after that, so this is where what part one covers, and then what we do next is that we again pass all of the document chunks in parallel to an LLM, and we also pass all of our properties to the LLM, and we ask it to extract relationships between the entities based on these two pieces of data. And once these relationships have been extracted, we can finally build a knowledge graph by connecting the entities using the defined connections between them, and then we store it into the database. So now we have a good understanding. I'll just do a quick walkthrough of the notebook to just give an overview of the code. So this is all of the core setup, installation, and then we are importing the required libraries, setting the keys, initializing the LLM, which is Gemini 2.5 Flash, which is, of course, like I said, it has a large context window and it's also fast, economical, perfect for this use case. And setting temperature to 0 makes sure that we have a deterministic output. We don't want creativity in this sort of task, right? Because we already have our data and everything. There's no creativity needed, so it's best to set a low temperature. So these are some utility functions for loading the PDF, for splitting text, and parallel processing connection to database. So then we load our document, and we can check that it has been loaded correctly. So for this example, I'm using my I was actually going just I was about to have my final exams, so I thought I'd use my cloud computing lecture notes, and maybe this will also side by side help me with getting prepared for my exams. So this is a large PDF. Like I said, it has 42 pages. It was, and it was a pretty large PDF, so I used this for the implementation. Then we connect to ApertureDB. By the way, this notebook that I'm just walking through, so this is based on the cloud version of ApertureDB, but I have alternate versions which are linked in the same notebook that are completely local, and you don't even need to sign up to ApertureDB cloud. You can just get them up and running. I have even uploaded some sample data sets, so it's super easy if you just want to test things out without any overhead or configuration. Then we upload. Now this is an optional step, but I feel like this is important. We can upload the raw PDF itself to the database as well, and connect it with our knowledge graph, so that later on, let's say if you have a question, you perform GraphRAG, you get your answer, and you're interested in seeing the entire document for some reason, that you can find the entire PDF. So we add our raw PDF to the database. Right. So now this is the what I talked about. We have now we're going to extract the high level classes from our our data, and we define the pydantic model to ensure that the LLM output is it's of a fixed format, and that it can be easily parsed. So this is super important, because we all know that LLM outputs they can be formatted in a very in various ways. So using structured outputs here is a very important part of this workflow, so that whatever output is given by the LLM, it can be parsed, and we can work with it in a deterministic sort of way. Okay, another important now, the core part is obviously prompting, and I will admit that it took a lot of tries to get this right, which is very standard trial. It's all about trial and error. You have to keep trying, iterating, and then you to finally get the output that you're looking for. In fact, the first thing that I started off with was, before I started prompting or anything, I first defined what I want the output to be like at each step of the workflow. So what I want the output to be like at the class extraction step, then at the entity extraction step, I did it in a sort of a pencil and paper sort of way. Once I had, I created this mind map sort of what the outputs would be like of one step, then next step, then and how the knowledge graph would be created. Then I went on to defining the prompts, what the prompts should be like to elicit those outputs that I wanted. So over here, I give the LLM overview of the workflow, and then I give it the task that you have to identify high-level general class types, and I give it all the instructions, what to do, not to do. I gave it the formatting instructions, and this can be thought of as a few short sort of workflow, because I gave it examples, so that these examples are very general, because this workflow is meant for a general sort of data. But again, for people who are already familiar what the data might be like, they can give more specific examples, and you can even constrict the what sort of classes should be extracted. But I kept it general, because I wanted to keep it open for all sorts of data. And one thing I just thought I'd like to point out is that why I gave it the entire context about the workflow was that, because when I didn't, it's sort of like a high achiever. It started doing even the other stuff that was to be done in the next part. So I specified it in each step that this is the current step. You just have to stay restricted to this step, and this was effective in stopping it from going over the top. Okay, so yeah, this was a prompt, and this was all defined. Then I passed it the data, and you can see that it has identified 16 classes. So all of the entities can only be classified into one of the 16 classes, and it has also defined, I haven't printed out all of the properties just to save space, but it has also defined all of the various properties that each class can have. Now the next step is extracting concrete entities for the classes that we have defined. Again, we first of all define the pydantic models to ensure that our outputs are super structured. And so this is to just make it more reader friendly. This is what the output should be like. So we have a class. Then for each class we have a dictionary of entities, and these entities themselves are dictionaries, where where we have the entity name, which is sort of like an identifier, and then for each entity we have the different properties. And again, I gave it these few examples so that it has a good idea of what the output should be like. And the instructions, they are very similar to the instruction for the classes, but of course this time they're focused on extracting entities. And I specify that entities should be concrete entities. And again, I also, if you can see here, that I mark the first step as completed, so that it doesn't try to do anything like that. And I specified that this is the current step. So again, this took a lot of trial and error, but eventually I got there. And yeah, so this is about creating the prompt. The next we have this is just a function to merge, because we're doing parallel processing here. So at the end we want to merge all of the results from the parallel processing into a single unified list. So we do that, and then we run it over the chunks as well as the extracted classes. We pass those to the LLM in parallel. So I split the document into 11 chunks. I defined the chunk size somewhere here. Hmm. Let me see if I can. Yeah, so I don't know where I defined it, but yeah, I just defined a chunk size. I think it was like 2000 characters or 1000 characters, something like that. Obviously, you can set the chunk size to whatever you want it to be like. And then it was able to extract 281 unique entities from the entire data. And these were all classified into one of these classes. So we can see here that the class which had the most which has had the largest number of entities is software. This class software layer, actually it's this one, cloud service, because obviously we have the nodes for of cloud computing. And then they're all different. These are all different entities, and this shows that for each class how many entities have been extracted, and these entities have their own properties defined as well. Okay, so in the next step, this is just some utility stuff that we have to do. We have to deduplicate the entities, because like I said, if you have the same entity in different parts of your document, you might have to duplicate instances. So you have to ensure that there is uniqueness, and then you can just deduplicate by by resolving the entities. So and then we also have to assign unique IDs to each entity, for which is very important, because for later for creating connections we use these unique IDs, and for GraphRAG as well we use these unique IDs. So we do that in this step. And for my workflow, I actually ended up not having any duplicate entities, um, but uh, but like, if because my notes were all, they were different topics, so each chunk had had different topics and no overlapping entities. But especially if your chunk size is very little, or your data is sort of like the same entity is being talked about in different parts, then you might have duplicates, and they will be deduplicated in this step. Like when I tried it off with some other data, then there were duplicates present. So this is an important step as well. I'll also just drop in this fact here that uh, for more enterprise outputs, for more enterprise use cases and all that stuff. What I've seen is that some use cases do multiple passes over the same data. They do multiple passes with an LLM, and then they resolve all of the common entities that have been extracted. So this ensures that the multiple passes ensure that if, let's say, the first pass you missed some entities, and in the second pass you can get them, and like that. In fact, there's this library lang extract um, which was introduced by Google a few days back, and they also have a very similar workflow again to this one, and they have built-in support for multiple passes. So that's something I found really interesting, and it's definitely for enterprise use cases to make everything more robust. Right. So once we have our entities, we can like insert them into ApertureDB. So right now they don't have any connections between them. We're just inserting them into ApertureDB. So we just run a query, and the best part is that ApertureDB has its own parallel loader, which is, you can see, it's just a few lines of code, and it handles all of the parallel processing by itself. We can just specify the batch size and the number of threads, and it does it all in the background. So you don't even have to like worry about it, and it's super fast. It took not even a second to insert all of these entities into the database using parallel loader. And yeah, I could confirm from the UI that all of the entities had been inserted, and I could see the distribution as well. Okay, now in the next part, we again give provider data to the LLM. For this time, we are going to extract relationships between the entities. So we define the pydantic model to restrict the LLM to give the specified structured output, and I will show you what the output should be like. So this again, now here is why I assign IDs to the entities, because now that we have these IDs, we don't need to name the entities. We can just give the class type and the IDs of the entities that have any connection between them. So what all we need here is that we need the source entity and the destination entity, and what relationship is between them. So this would be like the source is the source works at destination, right? So 1 works at 3. Similarly, um, 3 is located in 76. So this makes it very streamlined, because this also reduces the amount of tokens that the LLM would be generating, because instead of writing the entire entity name, it just gives this ID. And then you can easily use this ID to find the entities in your database. So yeah, was the same, in the same way as the other parts. I just did the same sort of prompting and gave it instructions on how it should do this task. And what we pass in here is we pass in our document chunks, as well as all of the list of all of the properties that we have from the previous step, so that when in each chunk we have the entire list of properties, as well as this particular chunk of document, and the LLM can then, whatever is based on whatever chunk it has, it can define the relationships in the entities that are present in that particular chunk. And again, we process, so this is for merging all of the we process these chunks in parallel, then we merge these into a single unified list. And yeah, so now when we run this, we can see that among the 280 something entities, we have been able to define 560 different unique relationships. So that's a lot of relationships, and that's what's really brings out the power of our knowledge graph and our GraphRAG pipeline. So these are some examples that have been printed out. So for example, this ID3, the entity with ID3, is an example of an entity with ID1, right? And by the way, although this print just shows that entities of the same class have relationships between them, but this is absolutely not a constraint. Entities of different classes can even have relationship between them. So for example, software layer can have a relationship or a connection with a computing system, right? So that's they can all be connected with each other, and the IDs help in uniquely identifying them. So now we have our knowledge graph defined in a textual manner. Now we just have to put it all together. So we had already ingested our entities in ApertureDB. Now all we do is that we use our IDs, the source ID, and we use the source ID and the destination ID to fetch these entities from the database, and then we add connection, whatever the relationship type is, right? The relationship type is taken here, from here, whatever the relationship type is, and then we also add some metadata, like what time this was created, what's the source class, what the destination class, what is the relationship type. So we do that. And this is also very useful, because these properties can further be used for filtering purposes. If you want to apply filters to your GraphRAG to only retrieve entities that have been inserted or whatever at a particular time or something like that. So this is very important for metadata filtering. Again, we ingest all of the relationships. We define the relationships in parallel using parallel loader, and yeah, this was also done in just 3 seconds, despite having so many different relationships. And we can confirm that we have all of the relationships. And then we can, if you remember, I talked about adding the entire PDF source to the database at the start. So if you had done that, then you can even connect each entity with the PDF source with this relationship belongs to data source. So it's like many to one relationships, like all of the entities are connected to a single PDF source with the relationship belongs to data source. So you can get their, if you want, you can get the original data, and then you can confirm that the how many connections have this have how many entities have this connection, and 281 entities, because all of them are connected to the data source. And this was something I did to actually visualize the graph using a Python library called NetworkX. So I fetched all of the entities and the connections from the database, and then so this was a graph. This generates a downloadable HTML file. So unfortunately, I don't have the downloaded file just now, but it's a very interactive graph. You can see, if you run the notebooks yourself, you will be able to see. You can zoom in and see all of the different entities and the relationships between them. It's just something to visualize it. And of course, there are even better ways to visualize, but this is just something that can easily be done. Yeah, so this concludes part 1, and now after that we'll move on to we'll be moving on to the part 3. But yeah, if there are any questions, then I could answer them currently. Okay, now that we have our knowledge graph in the database, the next step is to build the semantic layer by creating embeddings. So let's quickly walk through, get a high level overview of how that would be like. So at this point, we have our structured knowledge graph stored in the database, but we cannot perform GraphRAG over it because we don't have vector embeddings. So what we do is that we serialize the entities into text. So what we do is that we basically take these entities and all of their and on the for each entity we take the entity, we take all of its properties that have been defined, and we basically create these text documents. So each text document is basically um, is just a piece of, like, an entity with all of its properties, right? And then we create embeddings for each of these documents, which are basically just entities and properties. And then we create a vector index, which is in ApertureDB terms, it's a descriptor set. We create that in our database, and then we ingest these embeddings in parallel. And once we ingested them, we connect these embeddings to the originating entities, so that once we perform vector search, we can get the actual text as well, rather than just embeddings. So yeah, this is something like not too complex, but it's actually not too complex because ApertureDB really accommodates this entire workflow. So again, we do the entire setup, connect with the database. So now here we prepare entities for embedding. We fetch them from the database using uh, get schema method. We found all of the different entities we have, and we find all of their properties. So and then we create the entity documents. Like I said, we concatenate the entity, whatever the entity name is. We concatenate the entities with their we concatenate each entity with all of its properties, and then we add the entity ID as well to the document, and the class name as well. So this creates, so now we have 276. By the way, there's a disparity between this number and the number in this, because I think I was testing out and I deleted a few entities. I was just testing things out. So yeah, that's why there's a bit of disparity. Yeah. So anyway, yeah, we have these different classes, and all of these we have two. So over here is a sample of what the document, just to, like, I've been talking about it, but this is what each document basically looks like. So a document consists of the entity ID, whatever entity we're talking about, what the class of the entity is, and then we have all of its uh, properties here. So whatever properties it had in the database, they're all basically just joined together um, in a single document, which can be turned into vector embeddings and used in our vector search. So we do this for for each entity in the knowledge graph. Now in the the next thing to do is, of course, to generate vector embeddings. Again, you can essentially use any embedding model. You can use local embedding models, fine-tuned embedding models, whatever you want. I picked Gemini embedding model, and the dimensions are also configurable. So I went for 768 just to strike a balance between size and speed and accuracy. The larger the embedding, this is the more accuracy you will have. Then we generate embeddings. We can do it again in batches. So this is just some standard stuff that was taken from the Google documentation, and then our embeddings were generated. So this took like 3 minutes because I had to add some delay to respect the rate limiting. But of course, even this is quite fast if you don't add delays for rate limiting. And then once our embeddings were generated, I checked. This is just a sample. Obviously, it has 768 dimensions, so it's not feasible to, like, print them all. But yeah, all of the entities had their embedding, their corresponding embeddings generated. Next, we create a descriptor set in our ApertureDB instance. I named it entity embeddings Gemini, just for identification. So I use this query, find to create a descriptor set. I specified the dimensions, making sure that these dimensions are what the dimensions of the embeddings were, which are defined here. So these were the dimensions. Then this HNSW is the most common engine, and cosine similarity is the metric we're using here for vector search. These are the most like common ones, but of course you can even configure them based on your use case. So our vector index was created, and then we ingested the embeddings in the descriptor set by in the properties for identification was the source entity ID. Of course, the identity ID is the most important thing we're going with to identify each entity, and we also added add the entities class. So once that was done, all of the embeddings were ingested into the descriptor set, and this can be double checked here. After this was done, so now we have the entities we have the embeddings in the database along with the IDs, but we haven't made connections to the actual knowledge to our actual knowledge graph, to the actual entities in the knowledge graph. So in the next step we do just that, and this is super easy. We just find the entity. With the entity ID, we find a descriptor set with we find a descriptor with the same ID because they both share IDs, right? The embedding and the actual entity. Then we create a connection has embedding. So this entity has an embedding which is here. We do this for all of the entities, and we have 276 embeddings, 276 connections that have been inserted, and we can confirm it. So yeah, this is a part. This is like this was a part 3. This we have now created a semantic layer. We have our knowledge graph. We have our data. We have our the embeddings, and the next thing to do is to perform GraphRAG, which is what we've been building up for. Again, we do the entire setup, importing, defining the embedding model. Again, this is important that we use the same dimensions and embedding model for a query, because otherwise if they're incompatible, then vector search won't be performed. So we keep these things the same. So this is find some entry point. This is basically the simple KNN search. This is like at this point it is just vanilla rag. We just perform simple nearest neighbors k nearest neighbors search to find the top k most semantically similar entities, and then we when we get those embeddings of the entities, we find the actual entities, and then so this is just a formatting function, so that once we get all of the entities through a vector search, we can concatenate them into a single string which can be passed into the LLM. Okay, there now we come to, now this was just about vanilla rag, right? So now we come to the GraphRAG part, and this is over here we use we are going to traverse the GraphRAG. So for that we are using a BFS sort of graph traversal. So how that works is that, let's say we have fetched top k entities, and one of the top k entities is this purple one here. So what BFS does is that it goes to all of the entities that are connected to this one, and it fetches them. So it would fetch these and like this, right? Now if we have one hop traversal, if we have configured one hop, that means only these first degree connections would be fetched, right? But if we have configured it to be 2 hop, then even the connections of the connected entities would be fetched. So there will be 2 hops. Now for each connected entity, its connections would be fetched, right? In a BFS sort of way. Right, so this depends on how many hops we configure. Usually one is enough, because already you have a lot of connection, that might be enough, but maybe you can go to 2 hops as well. But beyond that, if you go beyond 2 hops, then you might end up with a lot of context. So this is again something that is very data specific. So this is just a function that defines all of this BFS traversal in the this is very data structure heavy. So I won't go into too much detail, but essentially what it's doing is that it is performing BFS over the knowledge graph that we have stored in our database. Again, the main thing that we're using is that we're using the source IDs and the destination IDs to find the connections. Then we add them to a set to see which ones have already been explored, and then we explore the connections. So there's 2 restrictions here are max hops and max entities. So what this does is that when either of these 2 is reached, we stop we stop traversing anymore. So let's say if we have configured max hop to 2 hops, right, and with the max entities that we have configured is, let's say, 15, right? So if we end up finding 15 entities in just 1 hop, then it will just stop. It will not go to 2 hops because we've already satisfied this constraint. On the other hand, if in 1 hop we only found 5 entities, so we will go to 2 hops, and then we found, like, let's say 8 more, so we have currently 13 max entities, but we will stop there even though we haven't found 15 entities, because the max hop has been reached. So you can again configure this based on whatever you want, and this gives you a lot of control. So you can ensure that maybe you want like 5 or 6 hops, but also you have a specific context size that you don't want to go over, so you can set the max entities here.
Aisha, we have a question from one of our audience members, Sona, and she asks, what about graph-like metadata that we might already have even before parsing the documents, or about the documents and other multimodal data?
Okay, that's a very good question. So for that, I already explained, like, when you define the properties. So currently what we're doing is that we are asking the LLM to define the properties, right? But if we already have some metadata, we can just prefix those properties to all of the entities, or to certain entities to which the metadata applies. So we can add them as properties of the entities themselves. So that's how metadata, I believe, can be handled.
Thank you.
All right. So yeah, this was about defining the BFS traversal and configuring it in different ways. And this is just calling that function. Okay, so now here I asked a query based on my document. What does a hypervisor do? This is related to the nodes. I configured the initial entity. So this initial entities are basically, this is corresponds with vanilla rag. This corresponds with top k. So what are the entities that should be retrieved using like vanilla rag, using basic KNN search, right? So once these k entities have been retrieved, next then we can go on to our graph traversal, and I configured max hop to 2 hops and the max entities 20 to be 20, right? So I pass that all into a defined GraphRAG function, and you can see that all of the context. So the first 3 entities are what were fetched through simple KNN vector search, but the remaining 17, because we have total 20, right? So the remaining 17 entities were through graph traversal. So this is but over here is a very important thing. You can see here that we were able to even fetch the connection between entities in our context to feed into the to the LLM, so that the LLM will have even more insight into what the connection between data is like, and it will be able to give answers to complex and nuanced questions. Then I finally passed this to the LLM, and it generated an answer based on the context. And one important aspect is the explanative. One important aspect of GraphRAG is explainability, because you can see here that we can basically, since we already have the entire graph basically of the fetched context, we can visualize it. So you can imagine that in enterprise use cases, we can show users, or it can be used, like we can use these insights to see why a certain answer is generated, what went into it, and what the background graph was like. So this is I believe a very important aspect, and it can help enterprises fine tune their graph and their workflow. So this is for baseline comparison. I also implemented vanilla rag, in which all I did was that I just fetched the top k most relevant documents, just top k, set S20, and then the same question I asked based on vanilla rag. Then I just chose 2 LLM judges, GPT-o3 and Gemini 2.5 Pro, and asked which is better, which response is stronger, and both said the response. This is not like a paid actor. They genuinely gave this response, that they found the response of the GraphRAG version better. But this was just one way, right? This was just one judging. So, but I wanted to do some evaluation. So again, I won't go into too much specifics of the evaluation, but I did 2 sorts of evaluation. So I started off with numerical metrics. So these are IR metrics, information retrieval metrics, which are usually used in IR systems: precision at k, recall at k, and mean average precision. So yeah, this is just a mathematical formula. So what I did was that I actually used an LLM for synthetic, query generation. I asked it to generate a few queries based on the documents, and then I asked it to map the golden IDs. Then so these are just some helper functions to get the IDs for this mapping. Uh, and then the definition and so then I ran the evaluations. But over here I like hit this roadblock. I just got a bit depressed because I was like, why is GraphRAG not doing worse than vanilla rag? Like I had done all this implementation and gone through all this trouble, and I it was like I thought that what was the point. But then I started thinking about it, and I was like, because this makes sense why vanilla rag won. And the reason is that because in vanilla rag, if you see, we are doing purely top k retrieval. We're retrieving top k IDs. So this is like pure vector overlap, right? Semantic overlap, and this gives vanilla rag an edge. What we're doing with GraphRAG is we're only retrieving a portion of the top key entities, and the remaining we're retrieving through graph traversal. So there's a less semantic overlap. However, we have more nuanced connections that go beyond semantic overlap, right? This is sort of this is a bit ironic, but this is sort of analogous to pure keyword search and vector search. So this is like the keyword search version of in that manner. And then GraphRAG is like the semantic search version. I don't know if that makes sense, but this is just to show that these metrics do not show the whole picture. So what I did next was that I used LLM as a judge evals, which I had been wanting to try out for long. What we do here is that we use an LLM to judge responses. So I for answer generation I used Gemini 2.5 Flash, and I use Gemini 2.5 Pro as a judge because it is a reasoning model. So if it would reason, then it might be able to give a better answer. So I asked it to just so for the answer generation, I asked Gemini, I instructed Gemini 2.5 Flash to just generate an answer based on the retrieved context. So I would pass in first, the GraphRAG retrieved context and the vanilla rag retrieved context for the same query and get the answer generated. Then for the judge model, I instructed it to assign a score. Basically, not assign a score, but just answer one or two based on what, like which. For example, if GraphRAG answer is better, then it should respond with one, and if the vanilla rag answer was better, it should respond with two. So I did that for each of the queries, and you can see here the very important thing I did was I set the temperature to 0 so that the answers could be deterministic and reproducible. One thing I'd like to mention is that when I curated these questions, I ensured that these questions are investigating deep relationships and and connections between whatever information is present in the data, which would really showcase GraphRAG's capabilities, because it's most useful when we are working with relationships between data. Just thought I'd like to I thought I'd mention that. Anyway, then I run these evaluations, and I found out I was pleasantly surprised and also happy to find out that in this evaluation, GraphRAG won. And you can see here that 8 times out of 10 the judge voted for GraphRAG answers, and only 2 times it voted for vanilla rag answers. So I ran it a few times as well, and setting the temperature to 0 ensured that I usually got like similar scores. But yeah, this showed me that that GraphRAG indeed won over vanilla rag, and it really validated all my efforts, and it helped show that sometimes maybe the metrics you're using might not be the most fitting metrics for your use case, and you have to like think about it, right? Like I first of all I thought that IR metrics are the standard, so of course I should use them. But then thinking about them, I decided, like I was able to realize that maybe for this purpose it's better to use LLM as a judge evals to get the full picture. Yeah, so that concludes the walkthrough of the notebooks. So yeah, I'll just I'll move on towards the conclusion. Okay, so right, I'd like to like go on to end this session by just saying that this was just a basic implementation. To be honest, there are so many ways that that knowledge graph and GraphRAG can be enhanced. We can use multimodal. We can like create a knowledge graph with images, videos, and all sorts of stuff. not just text. Then we can combine a vector search and we can apply metadata filtering. And this is something very important that I'm really super excited about. And what I plan to explore next is temporal GraphRAG. So this is something that is also becoming increasingly popular. So a very useful use case of GraphRAG is basically temporal reasoning. So you can filter data based on timestamps. Like if maybe at some point your data has become outdated, and using knowledge graphs with temporal aspect can really help you with that. And this is something that can be super useful in enterprise use cases. And yeah, you can scale it. And so Aperture TV itself is really optimized for all of these capabilities. Right. So thank you. That's all from my side, and I'll be happy to answer any questions. And I'll pass it on to Gautam now to continue.
Ayesha, thank you so much for this excellent walkthrough of your notebooks. I forgot to mention at the top of the hour that this presentation of the notebooks is based on a 4-part series by Ayesha, a blog, and so you'll get that as one of your links to the resources. So for a quick wrap up, we will have Gautam from Aperture Data just do a final wrap up, and then we can close our session for the day.
Thanks, Aisha. Yeah, and thanks, Denise. Yeah, that was like a pretty dense walkthrough, and I'm sure you have a well-deserved break. um, I'm just gonna keep this very short because we have already overshot the time that we kept out for the people who have joined in. But if there was like a one takeaway, I would want to have stamped onto the final call out for this presentation is this of course a LLM with a RAG enhances the responses of kept in a certain context, right? Like a general LLM would not be as good as answering things which are probably built with a vanilla RAG even. But what the graph really does to this context building is sometimes you don't have that semantic overlap. Like I have an example that just came into my mind and I put it as a diagram here. If one were talking about, let's say, question about a code base, which is my super application, and it has a bunch of things. It has a database, it has some kind of technology that is being built for its deployment, its infrastructure, and then it has some interfaces. Now, semantically speaking, and just from the probabilities of how these things relate to each other, there might be a strong correlation between databases and like ApertureDB Postgres SQLite as it's here defined here, and you might find them to be more similar in terms of the nodes. But with a different kind of nuanced connectivity between them, one could argue that a more richer response when answering the question about this application could be made available, just because they are all connected through the context of this application. So I I also would want to add to this. Another thing is that we have tried ApertureDB for graph lookups for really huge graphs. They might not be very meaningful graphs, but they were big in numbers, and we could just get some sense of how the performance scales out or looks when those kind of things are in play. And we have the 15 millisecond lookup with the billion nodes that we tried, and our vector, like the similarity search, has a sub 10 millisecond latency. uh, all these numbers were done with some kind of experimental. Usually I haven't come across the graphs that big. Our customers tend to be running graphs with some millions of nodes and that kind of scale. uh, but we have tried it for horizontal scaling also, and depending on the query complexity, you might have a, a good or more, slower or a faster response time. But yeah, that's pretty much it. And I'm going to conclude it here because I don't want to hold on to this precious lunchtime for people. And I'll call it the day.
Once again, thank you both Ayesha and Gautam for this excellent walkthrough on both your notebook. Great job. I want to also thank everyone who joined us. Thank you so much for spending your lunchtime with us on the session. And do as a reminder that you will receive this information on demand, as well as resources and links to all of the collab notebook and the slides that were presented. I hope you found the session useful. Would love to know your feedback, so drop us a note at team@aperturedata.io. And until the next one, once again, thanks Gautam and Ayesha for an excellent presentation.
Thank you for having me.
You're welcome. Welcome. Bye-bye.
Thanks. Bye bye.